Hello, my name is Burak Kantarci. I'm an associate professor at the University of Ottawa and a director of the Next Generation Communications and Computing Networks Research Lab at the University of Ottawa. So in this session, AI in ad hoc sensor networks and IoT, I will present our paper titled Deep Leaf Network-Based Fake Task Mitigation for Mobile Crowd Sensing Under Data Scarcity. So, mobile crowd sensing, it's a non-dedicated sensing paradigm, and it's very attractive because a large group of individuals can contribute to collaborative sensing of several tasks by using built-in sensors in their mobile and personal devices. So participants can submit sensed data by using the built-in sensors in those devices, and those devices can be their mobile phones, some tablets, or wearables. And the benefits of mobile crowd sensing are actually the elimination of the upfront commitments, and we don't need additional dedicated devices, so it complements the existing dedicated sensing services, and it lowers the cost of data collection. And of course, there's a mobility support because the users are moving around, and it can also provide some subjective assessments. But of course, those were the bright sides of mobile crowd sensing, but there are some vulnerabilities. So it is possible to have untrusted parties participate in crowd sensing campaigns. And also, the distributed sensing system is open for task submission and also for sensor data submission. So there's no prior information about the submitters, no predetermined or pre-existing trust relation. Now here what we tackle the fake task submission attacks in mobile crowd sensing environments. So the motivation behind the adversaries here in fake task submission is to clog the resources. And those resources can be the sensing servers or the participating devices, because by submitting fake tasks, well, the clogging servers are going to be busy with processing those tasks, and at the same time, the participating devices will be also consuming their batteries, draining their batteries, and also consuming other resources for processing, sensing, and also maybe with storage as well. Now, we would like to come up with an intelligent solution to detect those fake tasks and propose a legitimate path to distinguish fake tasks and legitimate tasks in mobile crowd sensing environments. Of course, there are some pre-existing studies in the literature, and they do use artificial intelligence methods, and they have shown that an AI-backed solution is going to be helpful to mitigate these type of fake task submissions. So these are the previous studies that can be used for either fake task submissions or data poisoning attacks. It's actually a different type of attack, there's a data poisoning attack. But in this paper, we limit our focus to fake task submissions. So what we basically do here is, this is our system model. So our tasks are generated by an existing mobile crowd sensing simulator, which is open source, and we provide the reference in the paper for this one. So this simulator generates the tasks. So those tasks can be legitimate or illegitimate. So we also have an attack model that we use to design the illegitimate tasks here. But this paper focuses on detecting the fake tasks, not generating. But we do have a study where we investigated the design and modeling of fake task submission attacks here at the simulator and how impactful it could be. So I encourage the interested audience to go through the reference list and see our previous work for attack design. Now, the tasks are generated by the mobile crowdsensing simulator. So a task consists of several features, say M features, and these tasks undergo a dimensionality reduction step. So here we use principal component analysis, and of course after the principal component analysis we have reduced dimensions here, but we have a mixed set of illegitimate and legitimate tasks. So we split the data set into a training data set and a task data set. So the training tasks will go into our deep leaf network model. But prior to that, we need to address two issues. Now, we need to address first the data scarcity. Now, here we don't have too much data. Now, what can we do? And the second challenge we're facing here is the imbalance, because we have lots of legitimate tasks in the environment, and the illegitimate or the fake tasks are the minority in this population. So what can we do? So here we have an oversampling step prior to our deep leaf network. So we use several oversampling methods before we decide which one would be the best one. I'm going to show you the results later on. And once we take care of the oversampling step, our tasks are fed into our deep leaf network for training purposes. And of course, our test tasks are fed into the trained deep leaf network, and the result is compared to the actual labels of these tasks that are previously known by our mobile crowdsensing simulator. So based on the results, we also introduce updates to our deep leaf network. All right, now how do we design the tasks? Now here we have 1,000 tasks, which is not a very big number. A task consists of an ID for sure, and a geolocation consisting of lat and long parameters, and of course a timestamp consisting of the day, the hour, minutes. And in addition to this, a task requires a duration feature. So how many minutes do we want that task to be sensed by the participants in that mobile crowdsensing environment? And we also need to know how much battery is going to be drained, how much battery power is going to be drained by this task. So the battery consumption, this is actually in terms of percentage of your total battery energy. And of course, there's one more field we need to know, which is the legitimacy of the tasks. So whether the task is legitimate or not. So this is actually the label of a data point. Now, how do we design and distinguish at the attack design stage the illegitimate and legitimate tasks? Well, the days vary from 1 to 6, so the experiments last for 6 days. And the hours for illegitimate tasks, well, majority of illegitimate tasks, they are submitted during a peak hour, so 7 a.m. to 11 a.m., so 80% of them. But of course, the rest are submitted during some mid-peak hours. For legitimate tasks, well, we have majority of them uniformly distributed throughout the day, and there's also a minority of legitimate tasks that are submitted during the off-peak hours, so from midnight to 5 a.m. And the duration, for the duration, as you can see here, 70% of the tasks, of the fake tasks, they last for 40 to 60 minutes, and 30% last for 10 minutes to half an hour. As for the legitimate tasks, well, they can last for 10 minutes up to an hour, and that value is uniformly distributed on this set. And for the battery consumption, 80% of these fake tasks, they drain 7 to 10% of the battery. And 20% of them drain 1 to 6% of the battery. For the legitimate tasks, 1 to 10% of the battery is drained, and that drain level is selected in our simulation. It's selected uniformly. So as I mentioned before, in our system model I presented, the data set is very much imbalanced. As you can see here, majority of the tasks generated by our mobile crowdsensing simulator are legitimate tasks, so there's nothing wrong with them. But there's a small minority here, like 10% of the tasks. These are fake tasks. And besides that, we also don't have too many data points. Now, what can we do here? Well, we try different oversampling methods. And we also would like to see the impact of dimensionality reduction prior to the oversampling. As you can see here, if we go with PCA for dimensionality reduction, well, the accuracy is going to increase. So for sure, going with dimensionality reduction, applying PCA prior to oversampling is beneficial. But which oversampling method is the most preferable one? Here, well, we need to run an empirical study for that, and here's the result of our empirical study. Well, here we have the borderline mode, so synthetic minority oversampling technique, and here the SMOD, original SMOD, and this is random oversampling, and here we have ADASN. So what we see here is if we go with borderline mode, borderline synthetic minority oversampling technique, we're going to have the highest level of accuracy in terms of detection of the fake tasks, or in terms of classifying tasks in the appropriate classes, like fake tasks versus legitimate tasks. So, all right, now we've selected the oversampling method. Now let's see the impact of the internal structure of the deep leaf network, because that's also an important parameter in determining the setup. So, first of all, we need to determine the number of inputs prior to dimensionality reduction. So we try 6, 7, and 11 inputs that have been mapped onto 4, 5, and 7 dimensions after the dimensionality reduction step, respectively. So this is the results. These are the results, as we can see. Right. So the best accuracy, these straight lines are the accuracy results. So we get the best accuracy under 7 inputs. 7 reduced to 5 dimensions. Okay. And these are actually the results after each run. All right. Again, we're going to stick with lower number of hidden layers. So there's no point in adding more and more hidden layers. So we can stick with 2 hidden layers. Okay. And what this tells us is that if we have 64 neurons in each hidden layer, we're going to get the best accuracy. So now we know the configuration of our deep leaf network in our system model to distinguish the fake tasks from legitimate tasks. So if we go with 2 hidden layers, 64 neurons per layer, and if we start with 7 inputs prior to the PCA step, we're going to get the best performance. And of course, our oversampling methods should be borderline mode. And this is also summarizing what I've just stated in the previous slide. So if we follow this recipe, we'll be able to achieve more than 92% accuracy and 94% precision, and more than 92% F1 score, more than 92% recall in the detection of fake tasks, or in the detection of fake tasks and distinguishing fake tasks from legitimate tasks. Now, what we're currently doing is we're using some other undersampling methods. We used oversampling methods here. We're using undersampling methods now. And we are also deploying some other machine learning algorithms for detection, and we are also seeing some promising results. But that part of the study started before, after this paper was submitted. So thanks a lot for listening. You can reach us if you have any questions. We'll be very happy to discuss. Thank you.